You are audible.
This call is now being recorded. So, we now continue with an exciting session in the quantum chemistry track. It is an honor to introduce Professor Himanshu Shekhar Biswal, an accomplished chemist and faculty member at the National Institute of Science Education and Research, Bhubaneswar. Professor Biswal's work focuses on the interface of quantum chemistry, molecular spectroscopy, and quantum mechanical model validation. His contributions have greatly enhanced our understanding of how theoretical prediction align with molecular level experimental data. In this fourth lecture of the quantum chemistry series, Professor Biswal will explore the powerful role of spectroscopic tools in validating quantum mechanical models, offering practical insights into theory experiment correlation. Let us warmly welcome Professor Himanshu Shekhar Biswal as he presents lecture 4 in the quantum chemistry series. The platform is all yours, sir.
Okay, thank you, Professor Roy, for the kind introduction. I also thank Professor Autry for the invitation and giving me a chance to give my lecture here. So I'd request the participants to actively participate in between. They ask, I don't know whether it is just login online or they are listening the lecture. So I need active participation. I don't know since it is not offline. I don't know whether they are listening or not. So I request all the participants to listen, and if there are some questions, please ask me without hesitation in between the lecture. So I'll be very happy to answer them. I'll try to answer all of your queries. So as introduced, I'm an experimentalist. We do a lot of computations. So the last lecture was completely computation, and this one will be the experiment, how we validate the computational methods. Sorry, we need to have a very specialized a technique to do that. Okay, so let me introduce, sorry, share my slides here. So is it visible? Sorry.
Yes, sir.
Yes, sir.
Okay. Yeah. Okay. So as the title says, validating quantum mechanical models with molecular spectroscopy. So I'll continue from my last lecture, and I guess I don't need to introduce you our institute once more. Just a brief introduction. So we are located east part of India in Bhubaneswar, and it's called the National Institute of Science Education and Research. We have many program like integrated MSc, integrated MSc PhD, and a PhD program in 8 different schools. And we have our own entrance exam called the NEST exam, which is going to happen in June 22. And from that exam, we select the students for the integrated MSc. We have a provision for to give them the fellowship, and the semester fees, all the stuff are very less in comparison to the IITs and IJs. So I request, this is just not only for the advertisement of Niger, it's for all of you, being the parents or the teachers. So please spread this one. There is the institute called the Niger, and we have this integrated MSc program. So yeah, so as I said, we do experiment, many different experiments, starting from the gas phase spectroscopy to solution to solid. We build our experimental techniques actually, which are not available, the equipment. And today I'll give a very detailed explanation or a detailed description about our equipment. So this is one of the equipment. We call it supersonic jet spectroscopy. I'll again describe in detail. So this spectroscopy has very unique, okay, in the sense this is one of the spectroscopy where you can have a mass selective UV spectroscopy, you can do mass selective biospectroscopy, you can do, you can go to a molecule level, you can select a single molecule or the two molecule like the dimer, homodimer or heterodimer, you can do the UV and IR spectroscopy, you can do the imaging. Okay, so it's a bit complicated. I'll tell in detail in next few slides. So now the spectroscopy what we have built, it took us almost 4 to 5 years to build the spectrometer, do the experiments working now, and we have lot of options like called the laser induced fluorescence, resonantly enhanced multiphoton ionization type or time of flight mass spectroscopy, fluorescence deep infrared spectroscopy, resonant ion deep, all the stuff we can do. And we are building something called the velocity map imaging, the polarized laser induced fluorescence. These are the stuff we are building to do many other spectroscopy. So as I said, the advantage, if you want to benchmark a quantum mechanical method, the quantum mechanical method, all of them, whether you do the DFT or ab initio calculation, you take a single molecule. For example, so if I do a calculation of water, right? So H2O molecule, I can find it out the normal mode of vibrations. There will be three normal mode of vibration, and these three vibration computationally you can predict, and then whether my level of theory is correct or not, how closely it is matching with the experiment, that will be that all the theoreticians who are developing the code, who are developing a method, they do it. They go for look for the experimental data and find a good match with their theory. Otherwise, if it doesn't match, then try to then modify, put some approximation or more prompts, so to modify those theory. So where do you get those experimental data? If you ask, or have you ever wondered actually where do they get it? For as a vibrational spectroscopist, I'll talk about the higher spectroscopy part only. So this one we get actually to do the calculation. We do the calculation of water, single water molecule. If you are familiar of using any software, let's say Gaussian, Gamesh or Turbomol, you just write the coordinate and give some what the level of theory. Basically, the level of theory, the basis set, or DFT method basis set, or MP2 or ATRIPOC. You just take the three atom, right? The atomic positions of two hydrogen and oxygen. So I have to do the experiment where I have to detect only one water. Okay. So if you do a solution, take a femtomolar concentration also for any of them, you will never have a single molecule. You will have plenty of molecule together, and you cannot take those data to match it to compare with your experiment, sorry, theoretical predictions. Okay. So that is actually to benchmark this one. You have to have a special technique to generate the data for the single molecule or dimer or trimer or tetramer. Then you can take those experimental data and benchmark your theory. This is the whole purpose of building those instruments. These instruments are highly expensive, highly time consuming, highly fragile. Many difficulties are there. So this is another spectroscopic method we are building here. This is called the matrix isolated spectroscopy. We treat actually in that case the other one, the supersonic jet spectroscopy. We have a single molecule. Okay, here we make argon matrix and we treat argon all these stuff. The noble gases, they don't interact with the molecule, and the molecule behaves like the isolated molecule. They are far apart from each other in the matrix, and that is another complementary technique to the supersonic jet spectroscopy. So this one has a lot of advantage. Mostly we try to study the chiroptical spectroscopy, mostly vibrational circle dichroism, electronic cycle dichroism at the single molecule level. So it have a huge, here also we have options for the frequency domain terra spectroscopy, and that is very useful uh, for uh, for uh, for the materials chemistry. So I have given few examples here how this frequency domain terahertz one can use to extract data in the terahertz region, like the optoelectric properties, real and imaginary part of the refractive index, dielectric constant, the conductivity, many other stuff we can extract. So this is another spectroscopy method which is recently developed, and the quantum mechanics at the molecular level actually is not that developed. We call the polarity chemistry. Here you have to have a fabricated cavity, and in that cavity you put the molecule, and if the cavity modes actually matches with your vibrational mode, then the molecule actually couple with this cavity mode, the vibrations, and the molecule will be another state. Like if you have photon exciting the molecule to the excited state, it will be another state. So here it happens with the vacuum coupling, and that there is very interesting stuff is coming. So molecule will either be in the molecular it will have a hybrid state. Okay. So then here is the other way around. People have started getting many different experimental data, but there is not a very accurate quantum mechanical theory to explain it. So those data are important, and the quantum mechanics is also developing to find to give a first principle explanation for those experimental data. So this paper I have taken actually very recently published, called the modification of ground state chemical reactivity via light matter coherence in infrared cavities. This is what we have developed. The technique actually it has a lot of problem with um, uh, the cell, all this stuff. It has a lot of problem. We have rectified and we have started getting some results, and maybe it will be helpful, or if some theoretician will be in the audience, so we can share with them with our data, and they will help us to give the quantum mechanical input of those data. So before I start, actually, these are just a brief introduction before I go to my lecture. So I am really lucky. So I have many brilliant students, hardworking students who spent a lot of their time to build the instrument. It's not that easy, as I said. So we have contributions from 42 students, whatever, and 14 different states of our country. And I'm looking, since I'm talking in Assam University, I'll be really happy if I get a student from that area. So if you look at in Assam, I don't have neither MSc student or PhD student. I'll be really lucky somebody joins in our group. So why the building scientific apparatus? As I said, it has a lot of usefulness, but you will find very rarely in India. People, mostly the physical chemistry, they come forward and build the equipment, and you'll find most of the equipment are built by the physicists. I'm talking about in India, and mostly why not the physical chemistry? Because we actually there are many, like NMR. You ask, you have a broker, all the stuff they send the build the NMR machine and sell it. Fluorimeter, UV visible spectrometer, everything is commercially available, and people buy. But there are techniques which are not commercially available. The most hindrance to build scientific equipment in India is the scarcity of motivated students, because our training is just a chemistry education. We will have synthetic organic chemistry or synthesis in organic chemistry. We never, in our textbook, we never introduce what is called fuse in chemistry textbook, what is called the connectors, many stuff. Okay. Even if we don't introduce also the different type of glassware in our curriculum, that actually one of the reason why students are not motivated to build the equipment. So it needs a huge funding. It has a huge funding, means the equipment I built, it is almost 4 to 5 crore. You need to have multi-skill task. So you need to have vacuum. I'll explain actually vacuum technology, electronics, many stuff you should have. You need to have a good mechanical workshop. Then since you are going to buy many stuff, many small stuff, you have to have a good cooperation from the purchase and account section. And the bottleneck, it takes 5 to 6 years to build a setup, which right, the PhD students will never come forward to spend his or her whole PhD life to build the setup. You will have multiple failures, so you'll have less number of publications and low impact factor. and it reduced the job opportunity. I tell it's the government job, but there are lot of since they will be skilled, actually trained, they get jobs on the elsewhere in the companies also. Some of my students are working in companies, so these are the demotivated part of the building scientific instrument. But I'll tell in the next few slides how it will be motivated actually, why the students working in my lab is motivated to build such equipment. So always it feels good actually to be the first to report something new which is not in the textbook in any of the journal. So you'll be the first. That is the strongest motivation to build the equipment. So I'll start one of the very simple. That's what I left in the last lecture. So it's called the hydrogen bonding. Hydrogen bonding, as I said, it is more than 100 years old. The concept. So, but recently in 2010, again, yeah, 2010, the International Union for Pure and Applied Chemistry, IPAC, they gave a new definition. They call it, I'm reading it, the hydrogen bond is an attractive interaction between a hydrogen atom for a molecule from a molecule or a molecular fragment XH in which X is more electron. I have highlighted in red, X is more electronegative than hydrogen. So please keep this statement in mind. X is more electronegative than hydrogen, and an atom or a group of atoms in the same or a different group, different molecule in which there is evidence of bond formation. So there are many criteria. So I was talking about those. You should have a binding energy. You should have electron density between two interacting atoms. So using the bond critical point, using the NBO analysis, those are evidences of bond formation. So if you look at X is more electron, is there possibility? So this is, you can have a hydrogen bond XHY. Y will be more electronegative than hydrogen. X will be more electronegative than hydrogen. If X is more electronegative than hydrogen, so you'll have a partial positive charge on hydrogen, and Y is more electronegative than hydrogen, you will have partial negative charge. Then there is the attraction between negative and positive. It gives a stable dimer. So is it possible? Now the question, is it possible to have MHY hydrogen bond where M is less electronegative than hydrogen? That means H will develop a negative charge and Y is also negative, less more electronegative than hydrogen. Then how is it possible to have a negative interaction, negative charge interaction? That's what I told. This is our perception. We did the calculations. Whatever I showed, we have taken the metal carbonyl hydrides. If you look at the charge calculations we did, the charge on hydrogen is minus 0.074 atomic unit. Here it is plus. Here it is plus. You look at this is negative. Okay. So if you take oxygen, again you take, here I have taken dimethyl ether, here the oxygen charge is also negative, but still it forms the hydrogen bond. Where is the problem actually? So is it our charge calculation is a problem, or whatever, uh, or any like the stabilization energy or NBO analysis? And is there any problem in the computational methods? Going by our conventional concept, conventional knowledge, you cannot tell actually. Two negative charges will come closer and give you a stabilization energy. But that's what we observe, and but there is no experimental evidence of this one. So this is what we published in 2019. Then there are few paper came in 20 after 4 years. This paper came, and they claim that they have experimentally observed that hydrogen bond, since the hydrogen is no longer del plus, it is del minus. So now from going from acidic, now it is hydridic. So MH we call the metal hydride. So they gave a name. It is called the hydridic hydrogen bond. This paper come in 2023, one of the best journal in chemistry called Journal of the American Chemical Society. After this paper published, then another group actually they said no, this is not, whatever you are telling is incorrect. So that's not called the hydridic hydrogen bond donor and not hydrogen bond donors. That's something else. They're telling it, see, whatever molecule they choose, there is another, the secondary interactions are there. It's not the interaction between the H minus and other stuff. Then very recently, this in 2025, to 1 2 months back, the people who are the professors who are involved giving the IPAC definition, they said actually whatever this paper Jax reported in 2023 is not also correct. So fortunately or unfortunately, none of them actually cited our work. So both all these three papers where we have categorically shown the calculation, we showed the H is minus and there is no secondary interaction, still it forms hydrogen bond. We need to prove it experimentally. These are the computations we need to prove it experimentally. And as I said, it has the spectroscopic signature. These are the computed spectroscopic signature, which we are going to use if we will do the experiment. We are going to use them, and if it works, then we'll tell actually this H minus, whatever you are telling, the H minus can form hydrogen bond. There could be hydrogen bond possible. So whatever I am showing, these are computationally calculated. Now, so if you remember, I introduced the IPAC definition. It is called the XHY. The Y is more electronegative than hydrogen. And recently we observed, actually computationally predicted, the electropositive atoms like tellurium and polonium. If you look at the electronegativity of a tellurium is 2.1 and polonium is 2. Okay, whereas this one is, so these are more electronegative, electropositive than hydrogen, but still they can form the hydrogen bond. Okay, so this one we again published. These are computational. Again, it has a IR spectroscopic signature. When we say IR spectroscopic signature, if you take this is my hydrogen bond donor OH, and the acceptor is the hydrogen bond donor, and the acceptor is dimethyl ether or CH3CO, then when we just monitor the IR stretching frequency, actually this OH vibration in the monomer, the vibration comes here. When it forms the dimer, this bond becomes weaker. Actually, this OH bond becomes weaker, and the stretching frequency becomes smaller. We call it the redshift. Okay, when there is a bond formation, hydrogen bond formation, there will be redshift of this OH stretching frequency. That's what we computationally monitored actually. If you look at, if you can have oxygen, sulfur, selenium, tellurium, polonium, and all of them has a redshifted. Okay, so this is well known. So methanol and dimethyl dimer is well known. Dimethyl sulfide is also well known. So, but the tellurium, polonium, still sulfur is more electronegative than hydrogen. It is acceptable. Selenium has almost same as hydrogen, but the polonium, tellurium and polonium, they are not same. Okay, so this is where we are actually interested in. Okay, whether my theory is incorrect or if I don't observe experimentally, that means the theory is incorrect. Okay, there is some spurious Hamiltonian is there, which is giving me the energies, and I have to correct. I have to take care of those. Okay, so that's why the experiment is still pending to verify it. So recently there is another controversy. Sorry. In chemistry, if the chemistry faculty, your students are there. There's something called the inductive effect. So I have a plus I effect or minus I effect. So generally it is known the methyl group CH3C. Okay, so this methyl group has a plus I effect. What does it mean? If you have a methyl group here, it will donate the electron to the attached atom. Okay. If I compare here HCr3 and methyl Cr3, if the charge in C is let's say X, for methyl one it will be X plus something. Okay. The electron density will increase if you have a methyl. That's what is the concept we talk about the plus I effect. And recently this paper published and they say going by the computation, by doing the charge calculation on this carbon atom, by substituting hydrogen with methyl other stuff, and they say this is not a plus I effect more, it could be minus I effect. And there is also another paper in chemical science. This is a very good journal also. They said actually the induction effect are our textbooks wrong. So they found actually some relation between the hyperconjugation. Or they're telling this is not the plus side effect of methyl is not because the charge development on carbon due to the methyl is not because of the plus side effect. It could be because of the hyperconjugation. Then this is the chemistry world, which actually highlights a very groundbreaking or something work in their paper, in their actually magazine called Chemistry World. So they wrote in it on 6th January, time to stop mentioning alkyl group inductive effects. Okay, so plus I effect is no more valid. This is this Chemistry World news came. So then we came into whether our predictions are wrong. Why people after 100 years people are using in organic chemistry? It is there in all the textbook. It is many organic reactions. So follow this one. You can explain many organic reaction if you consider methyl as a plus I effect group. What is wrong? Both the papers are computational papers. So here they have done a little bit of experiment, means compared with the experiment. But where is it wrong actually? Is the computation wrong? We came into this one. We started actually to finding out on whether we did many ways of doing charge calculation, about 20 different way of doing charge calculation. Here we have looked at the charge on oxygen atom. In water, if you look at the oxygen is bonded to two hydrogen atom, we have substituted one hydrogen with a methyl group. Okay, assuming that methyl group has a plus I effect, then if you compare water to methyl, the charge on oxygen should increase. Okay, but the previous one, the previous report, whatever I showed in the last slide, they did with the compare with the hospital charges, but if you look at here the charge is reduced, it's becoming more positive going from water to methanol. On the other hand, if you look at the molecule charge, it is the way we were thinking, it is giving the same way. Okay, so molecule says methyl has a plus I effect, hospital says methyl has a minus I effect, and it's bizarre actually. There is the Lodwin charge. If you compare, it's really they say the oxygen is a positive charge. Okay, and look at many of them, many the charge. The red one says it is minus I effect, and the blue one says it is plus I effect. Where which one is correct? Why do we need many charge calculations? Why we need many methods? Which some of the method is suitable for some experimental data or something. Is there any way to find it out which method is correct? Okay, so that's the whole objective and motivation. This is what we are trying actually this paper to publish. It was reviewed in many good journals. Unfortunately, since it is controversy, it is rejected, and hopefully it will be published soon. We face similar problem when publishing the metal hydride work, the work with the polonium, and I'm very sure we'll publish this work also. Okay. Why? So as I said, what we'll do actually to find it out, if I want to monitor the charge on oxygen, I have to have a probe. Okay, I'll take the hydrogen bonding as a probe. So if you have more charge on oxygen, there will be more attraction. There will be more attraction, means the OH bond will be more stressed, and you will have a more redshift. If it will be less charge, it will be less redshift. So if I do a complex with water and methanol, if methanol forms a stronger complex, means if it forms a stronger complex, I'll conclude that methanol has a plus, this methyl group has a plus I effect, and it gives more charge out to oxygen. That's why it forms a stronger complex than the water. So that is the idea, or vice versa. If it forms a weaker complex, then methyl group could be minus I effect. Now, I have to be short on that. In my experimental condition, there will be no environmental effect, no solvent effect. I will study only dimer. Okay, I'll study the monomer first, then I'll study the dimer, then I'll compare what is the shift from the monomer to dimer. That will give me the idea to conclude whether methyl has a plus side effect or a minus side effect. So this is whatever I told in the on the last slide. So this is what we monitor. This one we took actually the paracrystal this OH as the hydrogen bond donor, and we'll monitor this one in the monomer and the dimer, taking water and methanol or many other stuff. The problem is you have to make this complex. Okay, what we monitor? We monitor this wedge stretching frequency, which comes around the redshift will be around to 50 to 400 wave number, or the intermolecular vibrations. Okay, the molecule will vibrate, both of them will move. That is called the intermolecular vibration, which comes at 30 to 150 wave number. Okay. So if you look at the vibration spectra, actually, if you take this one, this paracrystal wedge in the most non-polar solvent like the cyclohexane or something, this is it is broadened about 300 wave number, the full width half maximum. Okay, I cannot use this condensed phase solution spectroscopy or solid state spectroscopy to monitor the changes happens. If your change is within the broadening, how can I conclude actually? How is it? What is happening? So for that, I have to take another alternative method called the high resolution spectra with very small pollute half maximum, low thermal energy. So I should have the thermal energy will be small, so that I will have sufficient number of the dimer. It will not break because of the thermal energy. I will have sufficient number of dimer in my experimental condition, so that I can monitor them. There should not be no solvent effect. If there will be solvent, there will be collision. You will not have a dimer. They will break. Actually, you will have a ensemble average. Whatever property you will observe, it will be average properties. You should have mass selectivity. I have to select the mass of this monomer. I have to select the mass of the dimer. Then I can record the ion spectroscopy. So these are the stuff I have to do it. So for that, there is no commercial equipment available. You have to build your own equipment. This is how this is what our equipment look like. So what we do, we call it supersonic gas phase laser spectroscopy or supersonic jet spectroscopy. We take our molecule, like here our molecule is paracrystal, then the monomer, we heat it, or if it has sufficient vapor pressure, we don't need to heat it. Then we introduce the buffer gas like the helium gas here. Then the helium gas and this one mixed up, that is called the pre-expansion. Then it expands through a orifice. Okay, the pulse valve, there is a pulse valve, and at the end of the pulse valve there is a orifice, very small hole of 300 micron to a vacuum chamber. We have two vacuum chambers. One is maintained at 10 power minus 6 torr, another is maintained at 10 power minus 8 torr. So you imagine here, before the pre-expansion, the pressure is about 1 atmosphere, about 1000 torr, and then it expands to a vacuum. Imagine if I have a syringe, okay, if I have a syringe, then I loaded this one with a liquid solution, okay, or injection, whatever injection solution. Then I press, right? So at the end of one end of the needle, actually, where there is the hole, you have a molecule, you have a liquid jet, and it works on in the same principle. One side is loaded with my molecule, which is highly diluted with the buffer gas. Then we expand this one with the orifice, and it expands through the vacuum, and it forms a molecular jet. Okay. Then because of the molecular jet, actually, it expands so quickly and so rapidly. All of the energy of the molecule actually transferred to the helium, or all of them goes to the translational energy. You will have a cooling of the molecules, the vibrational and rotational cooling. Here we can achieve the cooling about 10 Kelvin without using the cryostat. Just by doing the expansion, it is called the isenthalpic expansion. The principle it works called the Joule-Thomson effect, if you have heard of. Because of those isenthalpic expansion, we can cool down the molecule to 10 Kelvin till we keep the molecule in the gas phase, because the cooling happens so fast, the molecule doesn't get time to become close together and condense. So the molecule will be in the vapor phase, the molecule will have in the 10 Kelvin. So the molecule, the gaseous molecule will be so diluted. We take the middle part of this one to do the experiment. Then we put a skimmer here to select only the middle part. Again, we make a very selective molecule, the cold molecule, taking one molecule at a time. Then we use the laser actually to excite the molecule. One laser is used to excite the molecule to the ground state to the fast excited state. Then another laser is used actually, the second dye laser is used to take the molecule from the fast excited to the ionization state. Then we have the mass. Then if it is ionized, we have the electrodes actually to extract those mass. Then it goes to the detector called the channeltron or MCP. Yeah, before doing this one ionization, or we can do the fluorescence. We can collect the total fluorescence using the photo PMT, photo multiplier tube. So here we'll have the mass selectivity. Okay. So once we know the mass actually in the oscilloscope, we'll have the mass signal. We'll get the mass signal in the oscilloscope. Then you select the particular mass and we scan one of the dye laser. When there is overlap, when there is resonance from S0 to S1 transition, then we will have a huge mass ion signal. Okay, and that will give you the idea about the S0 to S1 transition. It is a bit different the way the UV visible absorption spectroscopy is done. It's we select the mass and we scan one of the laser, and where there is a resonance of S0 to S1 transition or energy match, then you have a huge mass signal in the oscilloscope, and we collect that ion signal, and that will give you the peak. So this is called, why is it called supersonic jet? So the jet actually expanded. The speed of the molecules are more than the speed of the sound in the vacuum. That's why it is called. It forms a jet, molecular jet. That's why it is called the supersonic jet. So I'll summarize. If you have any questions, you can ask. I have animations also. I'll show you a video. Supersonic jet spectroscopy is used to study the structure and dynamics of molecules and molecular clusters that have been cooled to 10 to 15 Kelvin but remain in the gas phase. Cooling the internal degrees of freedom, that is what I said, molecular rotations and vibrations, through the isenthalpic expansion of the molecular jet with speed higher than the speed of sound in a vacuum produces a highly resolved and simplified electronic and vibration spectrum. That I'll show you. This is how we do. If your sample doesn't have a sufficient vapor pressure, or it doesn't have this one, we use heat the molecule, or we do the laser desorption like this. We put another laser here. This is the graphite actual matrix. We make the molecule in the graphite one. Then we put the desorption laser. Then you have a plasma actually. Then then the plasma grows up. Then we expand the helium gas here. Then it takes the molecule. Here you have a hot molecule. During the expansion, the molecule cools down. It will have you can trap them at the cold condition in the global as well as the local minimum. As I said, you need a laser actually, the UV laser. The first laser takes the molecule from the ground state to the excited state. The second, the laser takes the molecule from the excited to the ion state. Then you have a mass signal. When you have an ion, you can have a mass signal. So before that, this is how we'll get the IR spectroscopy. The other way, you bring the IR laser before the UV laser. So what will happen actually? If you bring the IR laser before the UV laser, it will excite some of the molecule to the higher vibration state. Okay, so there will be depletion in the population of the B0, and you will not have the same ion signal what you are getting if there were no IR laser. Okay. So what we do actually, we monitor the ion signal fixing these two lasers, two UV lasers. Then we introduce the IR laser and we scan actually the IR laser. When there is a resonance, there is a transition from B0 to B1 or B0 to B2, then the population decreases at B0 and the ion signal decreases. Okay, so you will have a depletion in the ion signal. That's how we record the IR spectrum. So this is the whole setup. It looks like the way I explained actually. Here I have the sample holder. You have the orifice. Then I have we have two UV laser, one IR laser. then you have the skimmer, everything. Okay, so this is the experiment. What we can do in our experiment, cool down the molecule 10 to 15 Kelvin, reduce the spectral bonding and congestion, get the high resolution. The full width half maximum is over 5 centimeter involves. Study weak molecular complexes because the temperature is so less, right? 15 Kelvin, which is 20 times less than the room temperature. So with that we can study the weaker complexes. The thermal energy will be less actually. It will not break because of the thermal energy. So we can record, as I said, we can have mass selection and record the spectra. So as I said, it takes a lot of time. As you can see, I have to maintain the vacuum. I have to maintain the high voltage supply for the ion extraction. I have to keep the lasers running. So at least 60 to 80 components are there. Actually, very small components to build that setup. If one of them doesn't work, then you cannot do any experiment at all. So this is the difficulty of building such setup, and it's working now. We can do the experiment. So what I told actually this one, whatever I told, I'll show you in a video. We have written a software in LabVIEW called the Virtual Laboratory Experiment for the graduates. So you read it as village. We goes to the colleges. This one I have taken. We goes to the college, and who doesn't have access to this high-end equipment, you cannot take your equipment there. Instead, you can show actually what is happening, putting those photos, all the stuff. Here one of them, one module here we have studied the enzyme kinetics, and that we go to the colleges, schools, and so you can use this virtual software and do the to see visualize those experiments. So I'll use this software, and whatever I told, how we record the spectrum for the gas phase spectrum, and you will have idea. Okay. So do you have any question before I start the video? The video is about 10 minutes. Am I audible? Should
Yes,
I?
sir.
Yes, sir.
Okay. So I'll do whatever experiments we are doing virtually. I'll show actually whatever experiments I'm doing through the video. Okay. Okay. So before this one, I'll explain. This software is written by us. Everything is the instrument is built by us. Everything is done. So here, if you look at the top panel, it is written turbo. Turbo means pump, heater, the sample heater we use. Then the buffer means the helium or argon buffer gas. Iota means pulse valve driver. We have that valve is there, the solenoid valve. So it pulse actually, we don't have a continuous. Okay, if you have a continuous, then lot of helium will be lost. So you used a pulse valve. So that is called the iota. It is controlled by iota. So UV1 stands for the UV laser 1, UV2 stands for the UV laser 2, then the LIF stands for the laser induced fluorescence, that is the experiment we do. Then the PMD stands for the photomultiplier tube. Then the grid, actually the grid voltage is used to extract the ions. Then the mass detector, we have the channel tron or MCP. The REMP stands for the experiment we call the resonantly enhanced multiphoton ionization. This IR stands for the IR laser. Okay. So then, first of all, if your sample is not this one is not no, it doesn't have sufficient vapor pressure, then you have to heat it. Okay, so we can set the temperature and heat. That's what we call the nozzle temperature. If I switch on the turbo, this vacuum pump, I can see, look at the channel, the chamber pressure. CH stands for the chamber 1, the pressure chamber pressure 2. Then I can select the mass once I have ion. Then I can do the laser induced fluorescence. I scan the one of the laser, and I can record the REMP spectrum. Laser induced fluorescence and REMP has a difference. REMP has a mass selectivity where the LIF doesn't have. Then the current position, then we can do the spectroscopy. Okay. So I start the video. If you don't understand, you can stop me and ask the question. Okay. So carefully look at where the cursor is going, which one it is clicking. Okay. Is the video running? Can you see it? Yeah, the cursor is moving. Okay. So the turbo is on now. It become green. The pump, we switched on the pump. We'll wait to get the pressure actually here. the pressure like 10 power minus 7 in chamber 1, chamber 2. Then we set the temperature. The heater is on now. Yeah, you can see the red in the heater where I have kept the sample. Okay. Then we switch on the buffer gas like helium argon. Then we have a pulse valve. The valve is open now. Then you can see the this one, the molecular jet. Then we click the laser induced fluorescence. We click the UV laser. Okay. Okay. So there is a power actually. Power, the laser power. The UV laser is on now. Okay. So if you put more power, then you will have a scatter light. These are the fluorescence. We put the many filters, but still if you have a huge laser power, there will be a lot of scattering. So we try to reduce the power to get a very less scattering. Okay. So then we put the UV laser wavelength at one position where I have a transition to check whether I have a signal or not. We checked it, the signal is there. This is not a scattering. That's what the potential energy surface we click actually. We excite the molecule from V0 from the ground state to the excited state. Then we collect the fluorescence. Now we do the scanning, the laser induced fluorescence. The UV laser we are scanning. When there will be resonance, you will have a signal, the fluorescence signal. You look at the bottom panel, yes, there is a fluorescence signal. So we can see the fluorescence signal is at 35350, but that is not from the monomer, that is for the paracrystal water actually, the dimer, water dimer. Here we don't have mass selectivity. I have a band origin which is at a 35331. Yeah, so this is 35331 is the band origin, other one is the water cluster. So I don't have mass selectivity, that's why I am getting both paracrystal and paracrystal water. So to get the mass selectivity, only I need this spectrum, the paracrystal spectrum. I have to do the resonantly enhanced multiphoton ionization spectroscopy. For that, I have to switch on the grid. You can see the green color. Yeah, so if I increase the voltages, sorry, the UV power, you can have lot of fragmentation. We don't need that. We try to keep very less power of the fast laser. Then we go to the band origin position. Yes, you can see some masses there, but it is not a very high intense. So you can see the mass is 108, which is the mass of the monomer. This what is doing, we are doing here. Okay. Then we switch on the ionization laser. The UV1 is the laser from S0 to S1, UV2 for the ionization laser, which is fix it at a certain wavelength. Okay. Then the cursor is moving, we are selecting that 108 mass. Okay, nothing else. Now we select that mass and we select that signal. Okay. We go to the off resonance where you will not have any signal at all. Here we are changing the UV laser. Okay, so you don't have any signal. When there is a resonance position, then only you will have a huge signal. Okay, so LIF you had two peak, in REMP you have only one peak. Because we have selected only one mass, here is at 35331, you don't have any other peak. Here we have the mass selectivity where that one doesn't have the mass selectivity. Fine. Okay, so now we go to the paracrystal water. We change the mass position. UV laser the paracrystal water, which was 34874. Okay. Then we can select 126 mass. Okay, 108 plus 18 is 126, which is 18 is the mass of water. We can select the mass of water 126. Then we will start recording the REMP spectra of paracrystal water. So here you will not have a peak at 35331. Okay, you will have a peak at that band origin position. Yeah, this is very highly selective. This is called the 6A of the transition. Then you will have the sigma, the intermolecular vibration. Then you will have the band origin. You look at the load race. And this is called the sigma, the intermolecular vibration. All of them are coming for the paracritical water. I have selected, we are monitoring that mass only, 126 mass. Yeah, so this is coming here. Okay, so we found the big peak is the band origin peak, which is the vibration V is equal to 0 to goes to the ground state V is equal to 0 to the excited state V is equal to 0. So here I have mass selectivity. I can select the monomer, you have only one peak. I can select the dimer, you have other peaks with respect to dimer. I have mass selectivity of recording this the UV visible spectrum or the electronic spectrum. Now we'll go to the air spectrum. Okay. Now we'll switch off this one potential in the surface. I have mass selectivity, so we'll go to the UV position. UV1 position will keep the monomer transitions 35331. You have a monomer. Then we go to the mass 108. That is the monomer mass. We'll select it. Okay. Yeah, if you go to the IR transition actually, if there will be a transition actually going from V0, V is equal to 0 to V is equal to 1, then in the ground state itself, then there is a population depletion. You can see the mass is reduced, sorry, the signal is reduced. Okay, the mass signal is reduced. So we select that mass, the paracrystal mass, actually the monomer mass. Now we'll scan the IR laser. Wherever there will be a vibrational transition, there will be depletion of the mass signal, and you can have a inverted peak. Okay. Yeah, we'll do the IR scanning. We're changing the IR scale laser. Since there is no transition here, we have a transition that is corresponds to the wedge stretching transition. And when there is a vibrational transition, there is a depletion of the population in the vibrational ground state. That leads to the depletion in the population of the ion signal. So that's what we were observing. Fine. Now the next one, this one we select the monomer. Okay. So this peak is observed at 3658. Now we'll go to the paracrystal water. Okay, we first will fix the band origin, the S0 to S1 transition, that is 349874. Then that will come 126. You can see the 126 peak intensity increases because we have the electron transition corresponding to that dimer. Then we'll set the IR, actually the wedge stretching frequency corresponds to the dimer. Then it reduced. Okay. Now we'll select that mass, 126 mass. Then we'll do the IR laser scanning. And now you can see actually you will not have a depletion at 3658, you will have a depletion elsewhere, and that corresponds to the wedge stretching of the dimer. Okay, so we don't have anything. The 3658 went, we didn't have any depletion because we are monitoring the dimer. And now you can see a depletion. So now it comes less in energy. Actually, we call it red shift. It's almost 100, 120 wave number red shifted than the monomer. So that means that gives you an idea. Actually, there is a complex formation, and the complex formation happens through the hydrogen bonding, OH-O hydrogen bonding. So paracrystal has OH and water has this oxygen, and it is red shifted. So this is how we do the mass selective UV spectroscopy and mass selective IR spectroscopy. Okay, so all of you followed. If you don't follow, please ask me. I'll go to the next slide. Done. This is done. Okay. Any questions? Any questions? Can you hear me?
Yes, sir.
Okay. So I'll go to the next slide. Okay, this is by doing this show what we achieve actually. We did a lot of stuff. We designed this one. This is too expensive, time consuming, everything. So look at this is the fluorescence spectra of paracrystal in hexane. How broad it is. You look at this one. This is like the NMR peak. This is what we get it from our supersonic jet spectroscopy. So here you don't know whether this one, if you do the solution phase, you don't know whether it is coming from the monomer or dimer or anything. Here we can have those ideas. Similarly, if you look at the vibrational the weight stretching of the monomer dimer, it is too broad. Okay, the paracrystal, if you take the solution FTIR, too broad, but using our spectroscopy, you can resolve all of them. Okay, fine. So this is the advantage of using that spectroscopy. Now coming to our question actually. So as I said, so that is the plus I effect group. We started with the water, then we substituted to the methyl, and you look at going from the water, it is 127 wave number red shifted. Okay, going from water to methanol, it is 191 red shifted. What does it means? Methanol oxygen forms stronger hydrogen bond than the water oxygen. How it will form stronger hydrogen bond? If the charge on oxygen will be more, then it will form stronger hydrogen bond. So whatever experiments we did actually, the alkyl group actually increases charge, actually enhances the charge on the oxygen. That means whether you take methyl or ethyl or isopropyl or tertiary butyl, it is more and more red shifted. That means the alkyl group. If you increase the chain of the length of the alkyl group, there will be more and more red shift. That means more and more electron donation. So our experiment says it is plus I effect group. Whatever they have claimed, actually it's not valid through computation. This is very isolated experiment, very precisely done. In all the cases, it is observed that the methyl group has a plus I effect group. We didn't stop with this one. We substituted 2 hydrogen with 2 methyl. It's again more red shifted. If you have 1 methyl, then 2 ethyl also, it's more red shifted than 1 ethyl. If you have 2 diisopropyl, then it will be more red shifted. Okay. Then what we did actually, we did another control experiment. You take this one. This is a furan. You have the oxygen lone pair actually. The oxygen lone pair are delocalized. Is less available. Okay. So one by one we remove this double bond. Here I have a 2 double bond. The delocalization is more. That means there is less electron density on oxygen. In other case, it is more electron density. It is even more because it is still double bond is there, but there is no delocalization. So this is completely saturated. We did this experiment carefully. What we observe actually it is as you remove the delocalization, then the shift is more and more. So that means you have the alkyl group has a plus I effect. Then when we plotted actually checking these are the charges. This one if you take individually you calculate there is a very nice correlation. Okay, going from water to methanol to dimethyl ether. But that is the inverse correlation. Okay, so what they are telling the oxygen has more charge but less redshift, where methanol has a less negative charge but more redshift. This is very reverse in correlation what we observe. But we observed a very nice trend if you if you change the delocalization. Okay, so we found actually there is something wrong in the computation. I have to have benchmark. In one case it is valid, in the other system if you take it's not valid. So we came forward, give some empirical formula. Actually, if you take the electron, we see when you do the calculation, actually you need to take care of the electronegativity or of the nearby atom. These are the few corrections we proposed. If you take care of the electronegativity of here I have oxygen, in water it is bonded to hydrogen, in methanol it is bonded to the carbon. I have to take care of the electronegativity. The hydrogen electronegativity is not same as the carbon, so there comes the discrepancy. If you have carefully choose those, these are empirical. I am telling you, it's not derived from the first principle. So when we did the corrections, actually first one corrections, then the second, taking all the atoms connected to that oxygen, then we found a very nice correlation. Okay, whatever we are observing experimentally, there is no reverse. If your charge is less negative, then shift is less. If your charge is more, the shift is more. So what we suggested, the theoretical, whatever conclusions they have arrived, it's mostly because of there is some approximation in the theoretical method which needs to be looked at very carefully before we are telling something. Okay, this is what we proposed after validating the theory with the experiment. That's what my topic is. You need to have a proper validation of the theory before telling it the 100-year concept is wrong. Then we come to this one. This is a very nice textbook example called the aromaticity. Benzene is aromatic. Naphthalene is aromatic, but the cyclohexane is not aromatic. Okay, so there are many rules. I don't have time to go through it. So there are many ways to predict it, to find it out aromaticity. The question actually we are looking at, if you look at furan and thiophene, this is a very textbook example. People say which one is more aromatic, furan or thiophene? So people say actually the thiophene will be more aromatic than the furan because the electron delocalization in furan will not be will be less possible than the thiophene, because oxygen is more electronegative. It will try to keep the electron with the oxygen nucleus than the sulfur. If you look at the other, to have the electron delocalization, the oxygen has a 2p orbital, carbon also, this pi bond is a 2p orbital. So there is a possibility, there is energy match also. The delocalized orbitals, there is energy match. So they can that leads to the delocalization for the furan. Where if you look at the thiophene, the lone pair of electron is in the 3p orbital. Here the delocalized, the next bonded carbon atom actually contains the 2p orbital. The 3p to 2p orbital is less likely than the 2p to 2p. So there is counterintuitive explanation whether thiophene will be more aromatic or furan is more aromatic. So these are method actually in experiment. We use the chemical shift, actually the isotropic part. So chemical shielding tensor, actually we take a diagonalize, we take the principal component, and with some reference we find it out the chemical shielding. And with respect to the chemical shielding, we find if it is more aromatic, the hydrogen will be more deshielded, and it will come this one, the del value will be more. Okay, the pp. So that actually we then, this is a very textbook example. We included another. If you look at the selenophene, so neither this one, the selenium is the least electronegative, but the lone pair of electron is the 4p orbital. So there is very less likely for the delocalization. That's why our chemistry concept. So there are many quantum mechanical descriptor to describe actually whether the molecule is aromaticity or not. The HOMA is there, the many NPO, the NICs actually most of them people use the NICs. So if you take the NICs values, it says the order, the furan is very close to the selenophene and they are less aromatic than the thiophene. If look at the NBO delocalization, Selenophene is the least aromatic. Here the selenophene is the most aromatic. NBO says it is the least aromatic. Then which one is correct? This is again the experimental, lot of experimental data are there from the NMR calculations. We found actually the order is not same. The order depending on the different experimental parameter you look at, the order changes. And what we propose actually, if you instead of looking at the proton chemical, sorry, I don't have time to introduce this one. Anyway, so you remember this, looking at different NMR parameters, the order becomes different. So what we propose, if you look at the differences uh, of the chemical shift with respect to some of the atoms, then it can give a pre-order. The question we are asking actually whether the furan is most aromatic or selenophene is the most aromatic. So this is another paper. What it says actually, why are so many attributes, actually so many descriptors to describe aromaticity. Remember charge, we don't have a quantum mechanical operator to calculate the charge. Similarly, we don't have a quantum mechanical operator to find it out the aromaticity. So this concept actually depends on many other concept. That's why we have many results derived from many different quantifications derived from the many quantum mechanical methods. So we thought actually this interesting paper is there. We thought we'll do our molecular spectroscopy and see what we can do. This one I have already explained. If you have more delocalization, then the oxygen will be less, the electron will be less available for hydrogen bonding. You will have the less hydrogen bond and less redshift. So if you consider this one, furan will be the least, then the tetrahydrofuran will be the maximum redshift in the OH stretching frequency. That's what we did, and we found it out actually. It's very nicely correlated, looking at the charge and molecular electrostatic potential. Very nice correlation. Okay, so that gives actually gives us confidence to use the IR spectroscopy to tell actually whether there is delocalization is happening or not. So we did the same type of experiment, taking tetrahydrofuran, tetrahydrothiophene, and tetrahydroselenophene. These are saturated one, furan, thiophene, and selenophene. These are unsaturated aromatic one. If you compare actually, so it looks like the selenophene, okay. So the furan, the redshift is very less. In thiophene, it is a sorry, the furan it is a less redshift, thiophene is more, selenophene is even more. Okay. So what does it say actually? Okay, the selenophene, the delocalization is huge. Okay. Um, yeah. So furan, the delocalization is huge. Okay. So that's why. If the oxygen is less available for the redshift, right? So the redshift is less means there is less hydrogen bond. If the redshift is more, there is more hydrogen bond formation is happening. Okay. So we did the same thing for the excited state also. We found actually more and more redshift of with the selenophene than the furan and thiophene. Okay. So that means what we conclude actually the selenophene is the most aromatic than the furan and thiophene. Thiophene. So earlier what we are thinking, the selenophene, because of the selenium, it has a 4p orbital. There will be no delocalization at all possible, but it is possible. Okay, if you take the compare the saturated counterpart, so we are comparing minus 99 to 269 to minus 99. You are minus 285 to 94, minus 317 to 78. Okay, so here the delocalization is huge in selenophene in comparison to others, and that tells about the selenophene is the most aromatic than the thiophene. This work already published, and we have corrected how we can use the NMR data actually to give the accurate trend of aromaticity of those heterocyclic compounds. So I briefly explain whatever I told the BCD. This one I have already explained. So this one, what we do actually, we take a linear polarized light, then you use the photoelastic modulator, then we have a circular polarized light. If you have a chiral molecule, so it will absorb the left circular polarized light more and the right less, or in some cases vice versa. Then we take the difference between the left and right absorbance, and we get a the seed spectrum. It could be vibrational circular dichroism, or it could be electronic circular dichroism. So the setup we have the vibrational circular dichroism. So this one you can it has lot of advantage. uh, let's say if you have a phenylalanine where you have aromatic compound, then you can use the electronic CD. But if you don't have a aromatic compound, you cannot use the electronic CD. You have to be dependent on the vibrational circular dichroism. That's why we showed it here, D-alanine and L-alanine. The UV visible spectrum looks like this, but you can distinguish them. The chirality actually just oriented this one. The here the this amino group is up, this is the down. So this one we can distinguish by taking their the BCD spectrum. We have done actually for the camphor and this one. The camphor, if you take the ACD, you have a very broad band, only one peak. But if you look at BCD, you will have plenty of peak. If there is some interaction is happening, there is something happening in the molecule. Instead of probing only one peak, actually we can probe the BCD. You can have many information. Again, we want to use this one to validate many experimental data, which is sorry computational data, which is pending with us. So this is the technique we have recently developed. And this one will be used in the materials chemistry. Few of the studies people have done in the ECD using the CPL, but very less data for the BCD. We have started looking at those for the purpose guide. So as I said, we have a frequency domain terahertz spectroscopy. It has huge applications, yeah, in biology, in material science. So here what I said actually in IR spectroscopy, this intermolecular vibrations actually, these intermolecular vibrations comes in the terahertz within to 400 to 500 wave number, that you need to have a terahertz spectroscopy. If you have a crystal, co-crystal, if you can make, and if the crystal is not completely crystal, you cannot have a single crystal XRT. And that case, this terahertz spectroscopy of those co-crystal will be very useful to assign their structure. This is one of them. You take this urea and uracil. Urea and uracil, they don't have any absorption in this region, where the co-crystal have a very strong absorption. So these are very useful actually to benchmark the quantum mechanical method actually. So here what we did, we first thought there will be two dimer giving the terahertz spectra, and but it is not so. You have to take actually how many three pairs of dimer to have the spectra. This is how this spectra will be helpful actually to tell in my calculation, or which unit cell I will take, or how many dimers I will take to match with the experiment. So this is has many optoelectric calculations. We are writing our code actually to extract the optoelectric properties from those terahertz spectra. As I said, there are a lot of applications also. This one again, I skip this one. The polarity chemistry. We have they are huge. These are very recent papers. So we find actually this paper says material chemistry. If you have vibrational strong coupling, VSC we call, or light matter strong coupling in general. They have taken a metal organic framework, and they did the vibrational strong coupling targeting the wedge stretching frequencies. So they found the crystallization is accelerated because of the strong coupling. So here the even if the polymer can be conducting using the vibration strong coupling, this is from IIC. They say even if you have a polymer of benzyl methacrylate, then if you have a cavity, you can increase 6 orders of magnitude of the conductivity. many interesting stuffs are there. The theory is being developed actually to explain how is it happening, how can be a non-conductor becomes a conductor in presence of a strong light matter interaction. So these are the stuff of our experimental technique will be helpful to benchmark the developing theory or developed theory. So at the end, I should thank my students again and many who helped me the financial support from this one, and thank you for your kind attention. If you have any questions, I'll take it. Yeah.
Thank you, Professor
Sorry,
Biswal.
sorry. You
Thank
have
you
any
for your
questions?
Thank you for your informative and thought-provoking presentation. Your insights added great value to the session, and we truly appreciate the time and effort you put into sharing your expertise. We hope to have the pleasure of engaging with you again in future events. Thank you once again for your contribution. So now we will open the floor for question and answer. If anyone has a question, please feel free to interact with our expert now.
Good morning, sir. I have a question.
Good morning. Yeah.
Sir, in the second last slide, you have shown that the investigation of urea and uracil